Alright, welcome back to Inorganic Test Institute. In today's lecture, we are basically going to look at how we can understand the concept behind line integral of a scalar field. And also we will look at line integrals of a scalar field, but then with respect to or attached to the arc length. Okay, attached to the arc length as well. So let's begin with the integral of a scalar field. Right. So now, if we talk about integral of a scalar field, what do you understand by that? Okay, so I'm giving you some few seconds to reflect on that. Okay, so basically, if we talk about line integral of a scalar field, we are just talking about how we can add up values of a scalar function like density, temperature, and let's say pressure, okay, along a curve in space. Okay, that is basically what it means. Adding up, okay, how you can add up scalar functions like temperature, density, and something like pressure, okay, that are acting along a curve in space. Okay, so now I want you to think of this example, okay? Think of this example. Let's say you have a wire, okay? A very thin wire, thin one, a very thin one. Now, this wire is shaped like, we shape this wire like a three-dimensional, a 3D shape or a 3D curve. Now, at every point on this wire, there is a scalar field. At every point on this wire, there is a scalar field, okay? And this scalar field is defined for, let's say, for example, when you say temperature at that point, then if you want to, let's say, find the total heat along that particular wire or some other quantity like pressure or density weighted, okay, weighted along the curve, then you just have to compute this line integral. Okay, you just have to compute this line integral, and it is giving us this integral sign of a particular function f of x, y, and z dx. Now, what does this information tell us? This right here, f of x, y, z, is basically the scalar, is basically the scalar field, okay? This is the scalar field. Now, this right here, the ds, okay? The ds is basically some small arc length, okay? So this is a small arc length. This is a small arc length of the scalar along the curve. Okay, it is a very small arc length of the scalar along the curve. So we have to also know what this whole thing means. Okay, so basically the integral sign of this, the s, basically means that the the total accumulated value of the scalar along the curve. So this represents the total accumulated value along total accumulated value of the scalar along the curve. So that is basically what this means. Okay, that is what it means. So now I want us to move into the mathematical interpretation or mathematical definition of the line integral of a scalar field. Okay, so I want you to use this analogy. Let's say that the curve. So this is the mathematical definition, okay? So mathematically, we are going to deal with the line integral of a scalar field mathematically, okay? So mathematically, let's say that let the curve C, okay? Let the curve C be given by position vector R of T equals the angle bracket opened of x of t, comma y of t, comma z of what? T. That is the position vector, right? Now, let's say that this, that this is lying within a range of what? For R belongs to what? A and B, right? Inclusive. So that is the interval. Now, this right here, okay, this right here mathematically is equal to the integral from a lower limit to an upper limit of the function of s of t, comma y of t, comma z of t, right? Now, you have to evaluate the scalar function along the curve. So you evaluate the scalar function along the curve, and you know that this is the scalar function, right? So evaluate the scalar function along the curve. Okay, so you evaluate the scalar function along the curve. Now let's move on to this part. Then you find your ds, right? And we know that r prime of t, the magnitude of that is basically the rate at which arc length is increasing. Is the rate at which arc length is increasing. That is, it is the speed along the curve. It is the speed along the curve. So we say that the s is equal to the magnitude of the differential position vector, the magnitude of the differential position vector times the t. So this is how you find your what? Your dt or your dx, right? So that is the arc length. Now we know the informations right now, okay? So now let's take a problem to fully understand the concept behind line integrals of scalar fields. Let's have a short break and come back for a detailed example. Okay, so welcome back from the short break. Now, this is our first example that we want to take to very clearly understand the concept, okay? So, we want to evaluate this line integral, okay? Where C is the circular helix, okay? Given by x equals cos t, y equals sine t, and z equals what? T. For 0 less than or equal to t, less than or equal to what? 2 pi. So this is basically telling us the range or the interval for the integration. So we have to analyze this question well so that we can be able to work it out with ease. Okay. So first of all, we have to state our function. Okay, we have to state our scalar function. So our scalar function here, is this, right? The f of x, y, and z is y sine z. Very interesting, right? So from here, they said C is the circular helix given by S equals this, Y equals this, and Z equals that. So we have X equals cos t, Y equals sine t, and Z equals t, right? So we have that information as well, and we have our range to us. The range is 0 to 2 pi. Okay, so this is our range. Now we have to now go ahead and then evaluate the function f. Okay, the function f along the curve, right? So first step 1, evaluate f along the curve. Evaluate f along the curve. So from the question, we know that y is sine t, right? And z is t, right? And if z is t, then it means that note, if z is equal to t and y is equal to sine t, then means that z is also equal to what? Sine t. Very simple, right? So here our function is going to be f of x of t, comma y of t, comma z of what? T, right? And that will be equal to y is sine t and z is also sine t, right? And that will be equal to sine squared t. So our evaluated function along the curve is sine squared t. So we have our evaluated function to be sine squared t, right? So we have been able to evaluate our function along the curve. So the next thing we have to do, which is our step 2. So step 2, we have to find the arc length. Okay, so we have to find the arc length. And once we have the evaluated curve, the evaluated function along the curve, we can proceed, right? So find step 2, find the arc length along the curve, right? So we know that our position vector will be equal to s of t, comma y of t, comma z of t. From the previous, or from the beginning, or from the overview, we learned that r of t is equal to what? This, right? And we have s of t as this, y of t as this, and z of t as that. So our r of t will be equal to cos t, comma sine t, comma t, right? So that is our r of t. Now we need the arc length. So it means that we have to find r prime of t. Then we can go ahead and find the magnitude of that. Okay, so r prime of t will be equal to derivative of cos becomes negative sine. Derivative of sine becomes cos t. Derivative of t becomes 1. That's with respect to t, okay? So we have our derivative of what? The position vector. We need the arc length. So what do? We have to find the magnitude, right? So the magnitude of this will be equal to square root of negative sine t all squared plus cos t all squared plus 1 squared, right? And that will give us sine squared t plus cos squared t plus 1, right? Or dt. And we know that this is basically the arc length, which is the s. So the s will be equal to square root of sine squared plus cos squared is basically an identity, which is what? 1. So we have 1 plus another 1, right? dt. So we have the arc length to be square root of 2 dt. So we have the ds as square root of 2 dt. So what do we need next? Now we have already evaluated the function along the curve, and we have the arc length. So what we need, we just have to go ahead and set up the integral, right? We have to set up the integral. So that is going to be step 3. So we set up the integral. So step 3, set up the integral. Okay, set up the integral, and that is going to be this sine z dx equals We did that here, which gave us sine squared t, and our ds now is what? Square root of 2 dt. So times square root of 2 dt. And the range is what? 0 to 2 pi. Right. So we have our integral now. So we can easily integrate, right? So from here, we know that we can factor the constant out, which is the square root of 2. So we have square root of 2 out from 0 to 2 pi sine squared t dt, right? So before we can integrate this, we have to introduce the identity for sine squared, right? So from here, we know that, or recall that sine squared t is equal to an identity, right? Which is 1 minus cos 2t divided by 2, right? So that is an identity that you have to know. Great. So we're going to substitute this in place of that. So we have square root of 2 integral from 0 to 2 pi of 1 minus cos 2 cos 2t over 2 dt, right? So we can factor the half out. So we're going to have square root of 2 over 2 from 0 to 2 pi 1 minus cos 2 pi cos 2t, right? From 0 to 2 pi dt. So now we can easily integrate, right? So we're going to have square root of 2 over 2. Then integral of 1 with respect to t is t, minus integral of cos 2t is sine 2t divided by 2 from 0 to 2 pi. So now we are going to substitute the limits, right? So we substitute the limits. So from here, square root of 2 over 2 into, when you substitute 2 pi here, we are going to have 2 pi minus sine 2 pi sine 2t. We are going to replace the t with what? 2 pi. So we have sine 2 into what? 2 pi divided by 2 minus 0 minus minus or minus into sine into 0, right? So that is it. Okay, we know that sine 0 is 0, so we don't even need to do that part. Okay, so we're going to have square root of 2 over 2 into 2 pi minus sine 2 pi, which is 180. 180 times 2 is 180 times 2 is 360, right? And you know that sine 360 is 0. So we have 0 here, minus 0, minus 0. Beautiful, right? So here we have square root of 2 over 2 into 2 pi minus 0. And that is square root of 2 over 2 into 2 pi. right? And this is equal to 2 pi square root of 2 over 2. And clearly this takes off this, and we have square root of 2 times pi. So amazing, so amazing. So this becomes our final answer to the problem number 1. So one thing you have to know is that if you're asked to evaluate a particular line integral, and of course it's a scalar field, then first of all, evaluate the function that you have been given. Evaluate it and know that this is what you have and this is what you are going to integrate. Now, once you are done evaluating the function, 2, find your arc length. Okay, find your arc length. And before you can find your arc length, you have to find the position vector. And you know that the position vector r is equal to the angle bracket, okay? S of t, comma, y of t, comma, z of t. Then you close your angle bracket. So once you have the position vector, then you differentiate the position vector to have your derivative of the position vector. Once you differentiate that, find the magnitude of that, and then that becomes the arc length of that particular curve. Now, once you have the arc length, then you go and then find or set up your integral, right? Set up your integral, then you can go ahead and integrate. So beautiful, right? So that is the end of question number 1. Now let's move on to question number 2. But then I want you to have a very short break. I'll be back with question number 2. Okay, so welcome back from the short break. Now, with question number 2, it's just like question number 1, but I just made some little changes, right? And that is going to take us to a different level, right? So with this particular one, we are to evaluate this line integral, okay? But it's not attached with what? The s, right? This is cross x, not s. Okay, so it's going to take us to another dimension, okay? But it's the same preamble, okay? The same preamble as question 1. Now, with this particular one, we just have to set up our parameterization straightforward, right? So we know that x is equal to cos t, y is equal to sine t, and z is equal to what? T, under the range 0 to 2 pi, right? So this is what we have. Now, the question says that line integral y sine z dx, sine z dx cross x. So this is going to be y sine z dx will be equal to y sine z right? So we just have to find the x, right? And then substitute the z here with what? Sine t, because we know that if y equal to sine t and z is equal to t, that means that z is what? Sine t. So we have our function is going to be x here is cos t. So when you differentiate cos, you're going to have negative sign. So we have the s to be what? Negative sine t dt, right? So wherever we see the x in the function, we substitute what? Negative sine t dt. So we have this y sine z. The x now is negative sine t dt. So we have negative times negative sine t dt, right? So, and as well, we know that z is what? Sine t. So we're going to have from 0 to 2 pi, we know as usual our limit of sine t into negative sine t dt, right? So when we factor out the negative, then it means that we are going to have sine cube t dt, right? So this is all about this particular question. For this particular question, it's not what the s, it's not the s, it's cross x, so we don't need to find the arc length. If it is the x, that is where you'll be finding the arc length, but this is not what the s, this is what cross x. So you just have to differentiate the first component, which is what the x, then have your what the x and substitute and do your integration, and then you are good to go. So let's continue from here. So from here, we know that this is sine cube t dt, right? And sine cube has an identity, right? It has an identity, so we have to use it. If you don't use it, your work will be messy. Okay, so sine cube t dt is equal to sine cube t is equal to 3 sine t minus sine 3t divided by 4, right? So that is the identity for sine cube t dt, right? So once we substitute this in place of this, we can now go ahead and integrate. Abi? So we're going to have negative from 0 to 2 pi of 3 sine t minus sine 3t divided by 4 dt, right? So in here, we can factor 1 on 4 out. So we have negative 1 on 4 from 0 to 2 pi of 3 sine t minus sine 3t or dt, right? So we can easily integrate this, right? So we're going to have negative 1 on 4 into, when you integrate sine, you're going to have negative cos. So we have negative 3 cos t. When you integrate sine, you have negative cos. So we're going to have negative, we're going to do what? Positive. So we have plus cos 3t divided by 3 from 0 to 2 pi. So this is what we have. Now let's substitute the limits, okay? But we can see that both integrals are sine, and the integral of, and you see both integrals are sine, and they are over a full period, which is what? 2 pi. An integral of sine over a full period is what? 0. So when you look at this and you look at the limit, you don't even stress yourself to integrate. It will give you 0 automatically. When you have a sine function, okay, that is trying to be integrated over a full period, which is 2 pi, is going to give you 0. That is what you have to know. So when you have something like that, you don't need to what? Integrate. It's just a waste of time. So when you do that, you're going to have what? 0, negative 1 on 4 into what? 3 into what? 0 minus 0. So this will give what? 0. Okay, so note, if you have integral of sine that is trying to be integrated over a full period, you have what? 0. You don't need to stress to integrate that. So our result for the second example is 0. That is what we have here. Okay, so now what I want you to do is have a very short break, and I'll be right back with a couple of trial examples, and I will just leave the final answer for you to check it out once you are done trying your hands on them. Okay, I'll be right back. Okay, so welcome back from the short break. These are the trial questions. Okay, so I will expect everyone to go through the process so that it enhances your understanding. Okay, so I'm going to provide the final answers to each of the trial. So trial 1, the final answer is pi squared. So that is the answer for trial 1. Then trial 2, the final answer is, let me write it here. So answers. Trial 1, the answer is pi squared. Trial 2, the answer is 2 square root of 2 pi squared. So that is the answer for trial 2. Then trial 3, the answer is 2 pi. Trial 4, the answer is 4 pi squared. And finally, trial 5, the answer is 2 pi squared. Okay, so these are the answers to the trials. Please kindly go through the process and get the final answer. Once you get the final answer, please give a reaction at the comment section. Remember, I've promised, I said whoever gets the right answers should comment, and I'll give you shout out in my next video. So please make sure you go through them step by step. Okay, now let's move on to the next part of the section, which is line integrals of a scalar field, a scalar functions, but then in this case they are attached or with respect to the arc length. That is where you'll be doing a lot of parameterization when you'll be given different parts. Okay, so let's have a short break and come back for that section. Okay, so welcome back from the short break. I believe you have been able to go through the trial questions and it was pretty good, right? So we continue with the second section where we are going to look at line integrals of a scalar function with respect to the arc length. Okay, so with this one too, it is a scalar, right? But in this case, we are attached with what? The arc length. So it's the same idea, but we are going to go through different steps. The same idea, the same interpretation, but you are going to go through different steps. So in here, let me guide you with the steps that you have to follow to be able to arrive at the correct answer when you have a question of this nature. So steps involve. So step one, if you have the problem and it is with respect to the arc length, then first you have to parameterize the parts. Parameterize each part, okay? Once you parameterize the part or parameterize the curve, so parameterize the curve, let's say C, then after express, so that one is beneath under the parameterization. So express x, y, and z as functions of it, as functions of the parameterization that you did. Now, 2, evaluate or to plug in or put in the scalar field. Put in the scalar field. Then 3, evaluate the function. Then 4, and within that you find f of x of t, comma y of t, comma z of t. Then 4, you compute the arc length, which is the s, and that is giving us magnitude of the derivative of the position vector dt, right? Then finally you integrate over the parameter, integrate over the parameter interval, integrate over the parameter interval, let's say a and b inclusive. So these are the processes that you have to go through if a line integral of a scalar field is of a scalar function is with respect to the arc length, So first, parameterize the curve and express s, y, z as function of the parameterization, right? Then 2, plug in or put in the scalar field. 3, evaluate the function and then find the function of what? F of s of t, y of t, z of t, and all that. Then 4, you compute the s, which is the arc length. And this is how you compute that. Magnitude of the differential position vector times dt. Then finally, you integrate over the parameter interval. That is, the given interval is what? A and b, from a lower to upper limit. So what we are going to do is that we take a problem, okay, and then we will go through it step by step, systematically, so that even after solving one problem, I'll give you more trials for you to give your hand on them. So give me some short time, I'll be back with a problem. Welcome back from the short break. This is the problem that we are going to use to fully understand the concept. Okay, so this is basically quiz 2, question number 16, right? Quiz 2, question number 16, and this is code 1. Okay, so this is what we are going to do. We are going to use this problem to fully explain the concept. Then I'll give you about 5 trials to work on them with final answers. Okay, so we begin with this. So, the steps are here. Always try to get the steps so that it will guide you through the process. So first step, we have to parameterize the part, right? We have to parameterize the part of the curve, right? Now, there is this strategy that I always use. If the curve is basically a straight line, then this is how you are going to parameterize the part. But if it is not a straight line, then please, you have to go through the normal process. So if it is a straight line, the question sometimes becomes silent if it is a straight line. Okay? Or sometimes they mention that it is a straight line, and if it is a straight line, you see the points given this way, right? And then they will not give you any clue that this is a parabola or this is a circular something. Are you getting the point? This is a straight line, so this is what you are going to do. So this is a straight line, right? So the parameterization is going to be r of t equals 1 minus t times a plus t times what? B, right? So that is, the a is the first, we are taking the first part, the first segment. So let's say segment 1 from, let's say we are calling this a 100 to b of 010, right? So this is your a. So if it is a straight line, then you just have to multiply the starting point with 1 minus t, then the end point, which is the direction vector, by a scalar, right? So doing that, you're going to have, let's call this r1 of t. So r1 of t will be equal to 1 minus t times 1 comma 0 comma 0 plus t into 0 comma 1 comma 0, right? So you're going to have r1 of t equals, this will be equal to 1 minus t comma t comma 0 plus, yeah, so 1 minus t comma, because all of these are 0, you not have anything here, so comma, this here will be what? T, then we have 0. Okay, so this is our parameterization that we did, right? So the next thing we have to do is that, but please take note, if it is not a straight line, you don't have to do this. But if it's a straight line, then you just have to go through this simple process, then you get your what? Parameterization function, right? Note, if it is not a straight line, then remember that x is equal to s naught plus x1 minus x naught times t. Y is equal to y naught plus y1 minus y naught times t. Then z is equal to z naught plus z1 minus z naught times t, right? So if it is not a straight line, make sure that you go through this process to get your parameterized equation. So if you take from a of 100 to b of 010, that means that your s naught is going to be 1, right? Your s naught is going to be 1, and your s1 is going to be what? 0. Okay, So that is how you do it. And the same applies here. S0 is 0, Y1 is what? 1. Z0 is 0, Z1 is what? 0. So that is the process if it is not a straight line. So now let's focus on this problem. We have our parameterized equation now. So what do we have to do? We have to express x, y, z as a function of the parameterized equation. So we know that x will be equal to 1 minus t, y will be equal to t, and z will be equal to what? 0 from here. X is the first component, y is the second component, and z is the third component. So we have that. Third, or the second step, we plug in or put in the scalar field. So we are going to substitute this into the scalar field. This is the scalar field, right? So x minus 2y equals, our x is 1 minus t, and minus 2 into what? T, which is the y. So we're going to have 1 minus t minus 2t, and that is equal to 1 minus 3t. So we've put in the scalar, the x, y, and z into the scalar field, and we have been able to evaluate the function. So that is the evaluated function. Okay, so this is the evaluated function. So we have done the step 3. Step 4, we have to compute the s. So that is the derivative of the position vector, right? When we are done, then we find the magnitude times dt. So should I clean the steps? Okay, now we know the steps off head, so it should be off. So now our ds will be equal to r prime of t, magnitude of that, times dt. So r prime of t will be equal to, this is our r1, right? So r1 prime of t will be equal to negative 1, 1, 0, right? And then r1 prime of t, magnitude of that will be equal to negative 1 squared plus 1 squared plus 0 squared, and that is equal to square root of 2. So r1 prime of t is square root of what? 2. So it means that our ds is equal to a square root of 2 dt. So once we have that, the next step is to what? Integrate over the parameter in the interval. And the interval is from 0 to 1. From 0 to 1 because it's a straight line, right? So we continue with, we are coming to set up our integral. So from 0 to 1 of the scalar, the evaluated scalar field. So that is 1 minus 3t. And our ds is what? Square root of 2 dt. So we can factor square root of 2 out. So square root of 2 out, 0 to 1, 1 minus 3t dt. So let's integrate that. When you integrate this, you're going to have t minus what? 3t squared over 2 from 0 to 1. So we have square root of 2 into 1 minus 3 on what? 2, right? And that will be equal to negative square root of 2 over 2. Negative square root of 2 over 2. So that is the result for having computed the first segment. So we have to compute the second segment as well. Once we are done, then we add them, and that will be the accumulated value. That will be the accumulated value. Okay, so let's move on to segment 2. Okay, so with segment 2, with segment 2, we know that we are going to move from B of what? 0, 1, 0 to C of negative 1, 0, 0. Right? So with this one, we have to parameterize the part. And this as well is we know that the whole function is a straight line. So our R2 of t will be equal to 1 minus t times B plus t of what? C. Right? So we're going to have R2 of t to be equal to 1 minus t times B, which is 0, 1, 0, plus t of negative 1, 0, 0. Right? So we have R2 of t to be equal to, this will be 0, this and this will be what? 1 minus t. Then this will be what? Negative t, and this will be 0. Right? So that is for the second segment. So we have been able to parameterize the second segment. So what we have to do next is to plug in, right? We have to express s, y, z as a function of the parameterized equation. So we know that so we know that we know that we know that our s of t will be equal to negative t, our y of t will be equal to 1 minus t, and our z of t will be equal to what? 0. So the problem is here, so we have to evaluate that. So x minus 2y will be equal to negative t minus 2 of 1 minus t, right? And that will be negative t minus 2 plus 2t, right? And this, we can see clearly that this is going to give us, s minus 2y will be equal to t plus 2t is what? T. So we have t minus what? 2. Right. So that is for the second segment. We have been able to evaluate to have what? T minus 2. So the next step is to, compute the ds. And we know that ds is r prime of t, the magnitude of that dt. So r2 prime of t will be equal to negative 1, 0, right? So magnitude of that will be equal to negative 1 squared plus negative 1 squared plus 0 squared. And that is square root of what? 2, right? So our ds will be equal to a square root of 2 dt. So since we have square root of 2 dt for our ds, then the next step is to what? Set up the integral, right? So our integral from 0 to 1 of the evaluated scalar field times ds now is what? Square root of 2 dt. So we can easily integrate this, right? So we factor out square root of 2, then we have t minus 2 dt, right? So let's write this somewhere here, square root of 2, negative square root of 2 over 2. For the first segment, the result that we obtained, right? So square root of 2, t squared over 2 minus 2t from 0 to 1. And this we're going to have square root of 2 into 1 on 2 minus 2, right? And this is square root of 2 into negative 3 on 2. Right, so we have the second segment as well to be negative 3 on 2 square root of 2. So we add all to have the accumulated value. So we're going to add all. So we add all to have the accumulated value plus minus 3 on 2 square root of 2 minus 3 on 2 square root of 2, right? So this and this will give us minus 4 over 2 times square root of 2, and this will take 2 of this, so we have minus 2 square root of 2. So beautiful, right? So that brings us to the end of the problem. So our answer to the problem is negative 2 square root of 2. And that is the answer to question number 16, quiz 2. That is code 1. So brilliant, right? So now we have been able to know, we know the steps that is involved in doing this. So please remember if it is a straight line, okay, if the curve is a straight, if the scalar field is a straight line, okay, this line integral, if it is a straight line, then you just have to know that if you want to parameterize, it is what? R of t equals 1 minus t times a, the starting point, plus t times what? B, which is the end point. But if it is not a straight line, then remember, you have to go through the process. X is equal to x naught plus x1 minus x naught times t. Y is equal to y naught plus x y naught y1 minus y naught b, then t. So the same thing applies to the z. Okay, so if it is not a straight line, make sure that you go through the process to make sure you get the right parameterized function. Because if you get the correct parameterized function, that will give you the right answer through the process, because that is the first step and you are going to base on it to solve many problems. Okay, so now let me give you some short break, some very short break, and I'll be back. I want you to reflect on this problem. I'll be back with a tailored or some couple of what trial problems with final answers for you to verify your answer once you are done going through the process. Okay, so I'll be right back. Okay, so welcome back from the short break. I believe you have been able to reflect on the problem that we solved and you've really understood it well. Now, this is what you are going to do. I'm going to give you these 4 trials for you to try your hands on them, but I'll give you the final answer. Don't worry. And I'm going to explain them so that you know where to pass, what to do, and where exactly you will be ending at. Okay, so with the question number one, it says that you should evaluate this line integral, okay? And the question has been specific that it is what? A straight line. So as I said, if the problem is a straight line, then this is what you are going to do to parameterize your part. If it is a straight line, then your parameterization will be 1 minus t times the starting point, okay, plus t times what? The end point. Okay, so if you realize that the line integral or the problem is what? A straight line, then this is your how you get your what? Your parameterized equation. Take note, don't waste your time going through that lengthy process if this thing is there and it is a straight line. So note, if it is a straight line, this is what you do to get your parameterized equation. So you just have to face the starting point here, face the end point here, expand, then you know what to do, how to add them. That is so brilliant, right? So, however, if it is not a straight line, the question will let you know, and you will know that this is not a straight line. For instance, question number 2 or trial 2, the question says that you should evaluate this line integral where c is the curve y equals x squared from x equals 0 to what? X equals 1. So this clearly tells you that this is not what? A straight line, because this is telling you that we are talking about parabola. This is a parabola. So you don't need to what? Use a straight line approach. So this is a parabola problem and not a straight line. So you have to go through the process to be able to get your parameterized equation. Then with question 3, it also gave you that from this segment to this segment. So once you have the segment, that means that it is a straight line. You have been given the segment. Once you have the segment, then it tells you that this is a straight line. So you have to apply the formula and go. Question 3, question 4. The question says that it is what? A quarter circle of radius 2 from this to that. So this is kind of a blend of straight line and a circle. So this case, this is a special case, right? So with this one, you have to, parameterize using x equals 2 cos theta, y equals 2 sine theta, and you know that the s should what? R the theta. The s should what? R the theta. So that is how you do this particular problem. So now let me give you the final answers to the problems. So let me give you the final answers to the problem. So with problem 1, you have to get an answer to be, so answers to trial 1, you have to get 25 as your answer. So with trial 1, the final answer is what? 25. With trial 2, your final answer is approximately 1.635. Approximately 1.635. That is question number 2. Okay. And trial 3, your answer is 9 square root of 2. So that is for trial 3. And then for trial 4, your answer is 2 pi. 2 pi. 2 pi. So these are the answers to the problems. So with trial 1, you are supposed to get 25. So please go through the process and get the answer. With trial 2, your answer is approximately 1.635. And trial 3, the answer is 9 times square root of 2. With trial 4, you are supposed to get 2 pi. So this is what you need to know. So with question 1, the concept is what? Distance weighted scalar field, and along a straight line. So along a straight path, and you know if it is a straight path, you know what to do. The question 2, it is a scalar field along a parabola, right? So what you have to do is use the arc length formula along a curve. All right, use the arc length formula along a curve where y is equal to what? F of x. Then with question 3, is basically a straight path, right? So you just have to add the accumulated or add the contributions that you get from each segment, and that becomes your result. And then with question 4, you just have to parameterize the circle, right? As I said earlier, you have to parameterize the circle. using x equals 2 cos theta, y equals 2 sine theta, and then ds is equal to r d theta, and then you'll be able to handle this particular problem. I believe this is going to help you understand the concept of line integrals of scalar functions with respect to what the arc length. Thank you very much. I really appreciate your time. Please don't forget to subscribe, share with your mates, and I'll give you more updates. On to the next video. Keep learning and stay inspired. Bye bye.